great pleasure to introduce Michael Kapralov, who graciously volunteered to give an entire day of lectures on streaming and sketching algorithms. I'm very grateful to you for presenting for the day. This sequence of lectures today seemed like a natural bridge from everything we've talked about in the last 2 days about a bit more on graph linear algebra and graph data structures. So what we'll be doing in the next 2 days, talking a bit more about optimization and linear algebraic data structures, and talking about streaming and sketching as a natural bridge between all of these things. And thank you so much for volunteering to present for the whole day. So Michael Kapralov is a professor at EPFL who's done a wide range of works on sublinear time algorithms, a number of influential works on streaming and sketching, on graph processing, on sublinear graph algorithm design. And I think his work really, again, like so many of the speakers, fits well into the programs from the mix of work he's done on streaming and sketching and sublinear techniques and how exactly they've interacted things with spectral graph theory and algorithm design. So I think from all of his work, just by itself, he's well suited to give the lectures today. On a personal note, I am particularly excited for Michael's lectures and grateful that he agreed, because when I was a grad student, one of the main ways I learned about this area was by working with and arguing with you and listening to your many words of wisdom when I was a grad student. So I'm excited this will be recorded, and then in the future I can just point my grad students towards your lecture and have some of the experience. I'm also excited to maybe find out I learned some things wrong a number of years ago and I can have it corrected.
Awesome.
Anyway, thank you very much. I look forward to your talk.
All right, thanks a lot for the introduction. Thanks a lot for volunteering me for, for the marathon lectures on sketching. All right, so today I will talk about sketching. I will start by talking about some of the classical sketching techniques that were designed basically in the 90s and early 2000s with applications in data streaming in mind. Then in the second part of this, we'll move to sort of 2010s and see how to apply these originally data streaming techniques to solve linear algebra problems. And later we will talk about graph sketching. All right, great. So let's start sketching for data streams. So we will be talking about the streaming model of computation a lot. So let me introduce it to you. This streaming model of computation was introduced in a very influential paper of Alon, Matthias, and Zagade in '96. This was a paper on approximating frequency moments of data streams. More on that later. In the streaming model of computation, one thinks of the algorithm as observing a very long stream of data items. And at this point, these data items could really be anything. It could be IP packets, tweets, search queries, whatnot. Now, as the algorithm is scanning this very long stream of data items, it must maintain a small amount of state, so use a small amount of memory at every point in the stream. And at the end of the stream, or rather, really at any point in the stream, we should be able to stop the algorithm and ask it to approximate some basic statistics of the stream for us. Okay, so what are those basic statistics? And we'll get to this in a second, but a little bit more formally, let's define the model. We will think of single-pass streaming algorithms. That's the smallest number of passes that you can take over the stream. The algorithm will take a single pass over the data items. We call them I1, I2 through I capital N. We'll assume for simplicity that capital N is known. In some settings, you can guess it. In some settings, you can use an upper bound because we'll have weak dependence on the length of the stream. These data items, for the purposes of this talk, will really be numbers from some universe, 1 through little m. Okay. Now, as the algorithm is scanning the stream, it will maintain a sublinear amount of storage. So typically, it will be a low polynomial in the length of the stream, or really just polylogarithmic in the size of the stream. We will measure storage in bits, and sometimes for convenience in words, where a word is log n bits for some appropriate definition of n. We want our streaming algorithms to be fast, so when a new data item arrives, they should be able to update their state quickly. And most of the algorithms that we will talk about will be randomized. This is for a good reason. Most interesting streaming problems do not admit low-space deterministic solutions. So this is really necessary. All right, so what are those streaming problems that we are interested in solving? As I said, this is about approximating basic statistics of data streams. So today I will talk a lot about the heavy hitters problem. So let's formally define it. So here we take a single pass over the data items I1 through In. And besides the stream, which is given to us as input, we're also given a parameter k. And our task is to be able to output the k most frequent items that appear in the stream. Okay. These are known as heavy hitters. Good. We want to maintain a small amount of space as we scan the stream, and we will shoot for an algorithm with order k log n storage. Right. And some restrictions apply. We'll discuss what sort of approximation we get, et cetera, et cetera. But this is, in general, way better than storing all the items. So k is small. This is logarithmic in the length of the stream. OK, so here's an example stream. So our items, let's say, are from a universe of size m, where m is 10. So the items are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say the first item in the stream that arrives is 3, then item 4, 6, 3, et cetera, et cetera. So you see, as the stream is coming in, I'm also updating a frequency histogram for the stream. So far, element 3 arrived 3 times, element 2 arrived once, 4 arrived once, et cetera, et cetera. Good. So this goes on and on. Wonderful. And at the end of the stream, we realize that, say, element 3 arrived 6 times, which is the maximum. So if k is 1, then we're looking for the top most frequent element. We should be outputting 3, hopefully. Good. So this is the formal definition of the problem. A few words about the motivation. First, let's start with the motivation comes from the 90s. That's from analyzing traffic, internet traffic going through routers. So here's a router pictured on the slide. So a router is an object through which IP packets flow. And every IP packet, for our purposes, has a source IP address and the destination IP address. So you can really think of the distribution of packets flowing through the router as being described by a matrix. So here's this matrix. The rows are indexed by the source destination source IP addresses, the columns by the destination IP addresses. So that's a huge matrix. Now, before we turn on the router, the matrix is all zeros. Nothing has flowed through the router, and then the packets start going through it. As packets go through it, one can think of updating this matrix. Just record how many packets were going from a given source to a given destination. OK, so this goes on and on. Yeah, so we're looking at big data streams. So they're very long. OK, the stream is done. Excellent. So at the end of the stream, of course, most of the entries in the matrix are 0, but still a lot of packets typically flow through routers. So the number of non-zeros is very large, and way too large for the router to store the identities of the source-destination pairs. But now a question that a router might want to resolve is, what are the dominant flows? Which source-destination IP addresses exchanged a lot of packets? Okay, and this is exactly the heavy hitters problem. So in this particular case, the top 2 are these 4 and 5. Good. Why would we care about dominant flows, for example, to understand if there is a denial of service attack going on? Because in this case, usually a lot of traffic goes through a small number of source destination pairs. Good. So how can one imagine solving this problem? Again, the trivial thing to do would be to just store all the non-zero entries in the matrix. That's too much. And today we'll design the count-sketch algorithm of Moses, Chen, and Farah Colton that will give us an exponential improvement. Good. A little bit more about the motivations, or more of a 2000s motivation. Estimating search statistics in data streams. So imagine that we're given a set of items as a stream, say queries on google.com over a period of time. So hey, for example, here's a stream of my queries on Google some time ago. I'm looking for flights from Geneva to New York, then going for a coffee, and looking for flights again. And the most frequent items in this set would be Geneva to New York, because it appears twice. Okay. Good. So again, a trivial solution is to store everything, but that's prohibitively expensive in the context of queries on google.com over a period of time, but one can do much better, and we will shortly see how. Good. So one must add here that we will look at the asymptotic complexity, the asymptotic space complexity of these algorithms. But of course, a very natural question to ask is whether the constants are small and whether one can truly use these techniques in practice. The answer here is yes. For example, this is a different algorithm, but one can do cardinality estimation and data streams with very good constants. And similarly, CountSketch that we will discuss today is also used at Google, for example, for finding most frequent items in databases. Good. So this is the motivation. Now let's design the algorithm. Okay. Again, so we're getting a data stream, and we want to output the k most frequent items using order k log n bits, or actually words of storage. That's what we're going to do. Fantastic. Now, formally, this is asking to design a primitive that one could call find top. The task is to find the top k elements, most frequent ones in the stream. This primitive takes the stream implicitly as input and k, the number of elements to find. Wonderful. Now, however, it's more useful to think about a different primitive, which we called point query. Okay? Point query is the following. It's given a stream as input, and besides the stream, it's also given a data item I. And it is asked to return the number of times the item I appeared so far in the stream. Point query is an extremely powerful primitive. It really knows a lot. And if we have this point query primitive, then of course we can also find the top k elements in a data stream. That's pretty simple. We start by storing the first k elements. And then whenever a new element that we're not holding in our memory comes in, we just ask the super powerful point query how many times that element appeared in the stream so far. And if needed, we kick out one of the elements we store, and we put this one in. Excellent. So the reduction is very simple, but that's because point query is very powerful. All right. So in general, for simplicity, we will assume that our items are ordered according to frequency. So frequency of item 1 is the largest, F2 is the next, etc., etc. At this point, we're interested in designing this point query primitive that, given I, outputs fi exactly, and somehow we're supposed to do this in order k log n space for some parameter k. Now that, of course, is completely impossible. Okay, this is way too powerful. This is asking to exactly predict the count using a small amount of space. Imagine a stream where all items appear a small number of times, 1 or 2 or 0. It's information theoretical. Good. So that's clearly impossible. So we need to allow a little bit of approximation. So let's throw in some approximation. Instead of finding the top k elements exactly, we will find them approximately. So we'll call this find approximate top. Now it has 3 parameters, the stream, k, and epsilon, the precision parameter. We're now asking to return a set of k items whose frequencies are not much smaller than the frequency of the kth most frequent item. Specifically, what I'm reporting should have a frequency at least 1 minus epsilon times fk. Fantastic. That seems a little bit easier. Good. To achieve this goal, it would be enough to design an approximate point query primitive that, given the stream and an item I, returns an approximation, f hat of I. And this approximation needs to be epsilon fk close to the true frequency. All right. So that's what we will try to design. Except it's actually also not possible. Imagine again a stream in which all elements appear, let's say 0, 1, or 2 times. All right. If you look at the frequency histogram, it's very flat. So then this, of course, I allowed some approximation, but it's not really doing anything for me as long as epsilon is smaller than a constant. This is as good as exact estimation. All right, so in reality, we will design an approximate point query primitive except under the additional constraint that the stream is such that these top k elements that we're looking for contribute a non-trivial fraction of the stream in terms of their frequencies under some measure. And we'll get to the measure shortly. Okay. Any questions? Presumably not. Okay. All right. Excellent. So, that's our goal now. Indeed, we will be observing a stream of data items. Items come from a universe of size little m, and then we'll design a approximate point query primitive that will approximate f hat I, the frequency of I, pretty well. And we will specify the space complexity and all that later. We'll just design a nice primitive, and then we'll see which properties it satisfies. Good. So as I said before, we will only be able to design a good primitive under the additional assumption that somehow the top k elements in the stream contribute a non-trivial fraction of the stream. So it's good to introduce some notation for these top k elements. We'll call them the head of the stream. So here's a stream coming in. Here's its frequency histogram. And as promised, it is ordered in non-increasing order. So f1 is the highest. Suppose that our k is 4, and we're looking for the top 4 elements. These most frequent items we'll call the head, and we'll color them green throughout this lecture, and the rest we'll call the tail. Fantastic. To start designing such an estimate, I would like to ask a very basic question, which is, suppose that I'm only given a budget of one word, or one counter, to summarize the stream. How should I use this budget, one counter, to approximate the frequencies of data items in the stream? We'll design this basic estimate that uses a single counter, and it will turn out that it's a very nice estimate. So what can you do with one counter?
If you think of the items as strings, you could look at one bit of them, count.
I would just say, okay, I would say the most trivial thing to do if I have one counter to me is just every time an item comes in, I incremented my counter by 1. So I'll just compute the length of the stream. And at the end of the day, if you ask me what the frequency of item I is, I'll just look up the counter and I'll say it's this. Okay, that's what I have, all right? But it will do something that is somewhat similar, but actually critically different. Right? So instead of just counting the length of the stream, what we're going to do is choose a hash function that maps the elements of the universe uniformly at random to ±1. Okay? And our counter will start out as 0 at the beginning of the stream. And then when an item comes in, we'll simply increment the counter, not by 1, but by the sign of the item. Okay. Good. So this is our streaming algorithm. Fantastic. Now I need to give you the estimation primitive. At the end of the stream, you give me some I and ask me to approximate the frequency count. What do? Well, I can't just take the counter and give it to you because it could be negative, for instance. Maybe the stream contains my item all the way and it had -1 sign. What I do is I take the counter and multiply it by the sign of my item. So that's the type of estimator that will at least be good if the stream contains just my item and nothing else. Okay. Good. And what we would like to convince ourselves of is that this estimator is pretty good, that is close to Fi, the true answer, with some reasonable probability, at least for some interesting streams. So let's understand. So how are we going to do this? Well, first we'll establish that this estimator is unbiased. It's a randomized estimator. So first we'll compute the expectation, convince ourselves that the expectation is correct. And then we'll show that the variance is small, hopefully. Analyze the variance. Good. So what's the expectation of this estimate? So it's my counter times Si. What is this? The counter is just the sum over all positions in the stream of the sign of the item IP that comes in the pth position times S of I. Excellent. Now, that can be equivalently written as the sum over all elements J in my universe, number of times J occurred, which is Fj, times the sign of J. So that's how I was incrementing my counter when that item came in times Si. So there's one special term in the sum, which is when j equals I. So let me separate that out. So I get fi times the sine of I squared plus the contribution of the other elements, other than I. Fantastic. Sine of I squared is always 1. Great. And now it's clear that this very simple estimator is actually quite non-trivial. Because it is fi, we can think of this as fi, the true answer, plus some contribution from the rest of the stream. But let's look at this contribution a little bit more closely. So imagine for a second that the stream is like this. The item I that I'm querying maybe is the heavy hitter, the most frequent item in the stream. Right? And imagine also that the other items in the stream all occur a bounded number of times. So the frequency histogram is sort of benign in the sense that I have one item sticking out, and then the rest are pretty flat. Now, so think of these fj's as small constants. Now the signs sj are random. So the sum here will actually have a lot of cancellations. Right? And so this is what makes this estimator with random sign distinctly better than the absolutely trivial one, where, okay, I have one counter, I just sum up the length of the stream. Okay? And that'll be basically where the power of count sketch is coming from. All right. Good. Okay, so now let's analyze the expectation formally, right? We'll just put expectations on top of this. Now the signs are purely random. Really, pairwise independence is enough here. So the expectation here is 0, and indeed the estimator is unbiased. Fantastic. So now, what is the variance? I want to convince myself that the estimator is actually close to fi, or with high probability, whatever that is. Right. Good. So what is the variance? Well, the variance of a random variable is the expected squared deviation from its mean. Amazing. We know that the mean of our estimator is fi, so really we're interested in the expectation of the squared contribution from the other elements j that are not I. Okay. So we just open up the square. What do we get? We get a sum over j and j prime, both different from I, product of frequencies, fj prime, times sine of j, times sine of j prime. And si squared, this is 1, so nice. Good. So now, if we look at this, we realize that if we consider the terms corresponding to j distinct from j prime, then again, these signs sj times sj prime are 0 in expectation. Again, even if the sign even is just pairwise independent. Excellent. So the variance is really governed by the diagonal terms, and so the variance of the estimator is nothing but the summation of the squared frequencies over everything but I. Good. So that's what we proved for the variance. The variance is the L2 norm squared of the rest of the universe. And so by Chebyshev's inequality, with high constant probability, our estimator is about the L2 norm of the rest of the stream close to the true value. Okay. Good. So the question is, this seems nice. It's nice for these streams that contain a single element, and then the rest is pretty flat, as I mentioned before. But is it good for everything else? Not clear. So let's think about this. So again, here's a picture illustrating my previous point. If the item to be estimated is the heavy hitter and everything else is pretty flat, then we are in a fantastic shape. But of course, if we are estimating an item that actually is actually low, then the estimator is corrupted by the heavy hitter. So that's not good, and we need to fix it. How do we fix it? We'll fix it by hashing. What we're going to do is partition the universe into random subsets of appropriately chosen size, and we'll run the basic estimator on these hashed or subsampled streams. This will make sure that we will estimate, we'll never be in the bad position. Good. So this brings us to the count sketch algorithm of Cherikar, Chen, and Farah Colton. The main ingredients are to run the basic estimate on a subsampled or hashed stream. So this will reduce the variance of the estimator. And then we'll do some aggregation using medians. We'll repeat this experiment a bunch of times to make sure that the error probabilities are low. So here's a pictorial representation. Here's our stream. There's the head of the stream and the tail of the stream in red. Note that this is the universe, not the stream itself, and we're hashing it into some number of buckets. For example, if we hashed our universe of size 10 into 8 buckets, then we get 8 subsampled streams. Each bucket corresponds to a substream. For example, the subsampled stream of item 1 is all occurrences of 1 and 6. Because there is a collision in this orange bucket. Similarly, the subsampled stream of item 5 is all occurrences of 5 and 7 because of this collision. Just to repeat again, we're hashing the universe, not the positions in the stream. So, for example, substream of 1 is all occurrences of 1 and 6, so that's 1, 6, 1, 1, 1. And similarly for 5 and 6. Great. So let's summarize. This is our final count sketch algorithm. We will choose some parameter t, and select t random hash functions, h1, h2 through ht. All of these hash functions hash items from our universe M to capital B buckets. We'll decide how big B is, but you should really think of B as roughly K. Recall K as the number of elements is the number of heavy hitters that we're trying to find. Okay, and we'll also select, of course, the t-random hash functions, S1, S2 through ST. So basically, we're just doing t independent repetitions of our basic estimate in the hash buckets. So the data structure that the algorithm will maintain is simply an array. So here's this array on the slide. It has t rows and capital B columns, the buckets. And the t rows correspond to independent repetitions, and the columns correspond to the subsampled or hashed streams. Here's the actual algorithm. Upon receiving an item, let's say item 5, arriving in the stream, what the algorithm does is simply goes through all the t rows in the array. For every row r from 1 to t, it checks where, it applies the hash function, the rth hash function, to the item arriving, looks at hr of I, checks where the item goes. So let's say 5 goes to this bucket in the first row, and increments the corresponding value by the rth sign of the arriving item. Indeed, just run the basic estimates on the substreams. Okay. Now, once at the end of the stream, we're asked to approximate the frequency count for some item I. What we do is simply take the median of all the t estimates over the rows. Any questions about the mechanics? Good. Good. So let's state the actual precision guarantees of this algorithm. So we'll prove the following lemma. If the number of buckets, B, is sufficiently large, and sufficiently large here is B is at least a constant times K, and at least something that depends on the ratio of the L2 squared norm of the tail and the head, so to speak. Almost. We'll get to this in a second. And if the number of independent repetitions is chosen to be order log n, then we get good estimates, where good is additive error at most epsilon times the kth largest frequency fk, simultaneously for all elements of the universe at every point in the stream with high probability. Good. So we'll prove the lemma. But before proving the lemma, so let's note that the space complexity of this is order b log n, right? Because log n repetitions and b buckets in every repetition. At the same time, I advertised an algorithm with a space complexity order k log n, so we need to convince ourselves that b is order k, at least in these natural cases that my asterisk there mentioned. Good, so how large is b? Essentially, it's a question of, let's understand the second term in the max. All right. At this point, we exactly come to this formalization of the claim that I made at the beginning of this talk, that we will get an algorithm with space complexity order k log n if the top k elements in the stream dominate the stream under some measure, or at least provide a non-trivial fraction of the stream. Good. So here's, again, a pictorial representation of the frequency diagram. And let's imagine that the L2 squared norm of the tail of the stream is comparable to the L2 squared norm of the head. Okay. Or even more specifically, here, since we insist on our error being epsilon times fk, let's take the total L2 squared norm of the tail and partition it equally between the top k elements. If this equal partitioning of the total L2 squared norm does not swamp the kth largest element, then we get exactly the right precision guarantee. So essentially, as advertised, if the top k elements provide a non-trivial fraction of the L2 norm, then we get the result. There's one other nice formalization of this. Note that in general, as long as we choose b to be at least k, the number of buckets we choose to be at least k, then the errors on the counts that we get are at most square root of 1 over b times the L2 squared norm of the tail. We'll see this a little bit more formally in a bit. Good. All right, so now another note on the space complexity of the algorithm, getting back to my model example where the stream contains a single heavy hitter and then all the other elements arrive with roughly a constant frequency each. Suppose that k equals 1. So we're just looking for the heavy hitter in a stream. And suppose that this element 1, the heaviest one, appears square root n times in the stream, and all the other elements in the stream are distinct. Okay. Let's figure out what the space complexity of finding this element is using count sketch. So f1 is square root n, and fi is 1 for all the rest of the i's, of which there are at most n. Now, the total L2 squared norm of the tail is therefore at most n, whereas f1 squared is n as well. So this ratio in the second argument of the max is actually just 1 over epsilon squared. And this, I claim, is very surprising because this heavy hitter appears in a vanishingly small fraction of the stream. There's a polynomially small fraction of the stream, just square root n positions out of n. So there's absolutely no way you can find it, for example, by just sampling the stream. Nevertheless, using count sketch, we're able to find such an element using only a constant-ish amount of space, or up to some logs. All right, fantastic. So these are just some instantiations of the bound. Let's just formally prove the lemma. And the lemma is, again, that if b is at least k times the is at least the max of k and the ratio of L2 norms, tail to head, so to speak, then we get good estimates. All right, so what governs the quality of our estimates? Oh, it's basically just the variance of our basic estimators that we run on the subsampled stream. Let's fix some element I, and let's fix a row R. All right. Let's understand the precision of the estimator. for I given by the rth row? Well, by the basic estimate analysis that we did before, the variance of this estimator is the L2 squared norm of the corresponding substream. So the sum of squared frequencies. If I sum over those j's that hash to the same bucket as I, and I also ignore I. Great. And we'll show that with high constant probability, this variance is just a 1 over b fraction of the total L2 squared norm of the tail. This is natural because we're hashing into b buckets, so something has to go down by a factor of b. There's one nice point to make here is that this is not the total L2 squared norm, it's the L2 squared norm of the tail. That will have nice implications in a second. Good. So to establish this bound, what we do is we look at the variance as a sum of two terms. The first contribution comes from the head of the signal, the green, the dominant elements, k of them. And again, we only look at those that hash together with I in the same bucket in the rth hashing. And the second term is the same for the tail. All right. So for each row and each item, we define 3 events. First event is the event that our item I does not collide with any of the head elements. Recall that there are k elements in the head of the signal, and we're hashing into b buckets, and b is at least k with a large constant. So that will happen with good constant probability. There's a small variance event, and that's the event that the variance corresponding to i's bucket is about a 1 over b fraction of the total tail. That will follow by Markov, and some small deviation event, just meaning that the basic estimator analysis works. We'll show that all of these 3 events hold simultaneously with probability strictly bigger than 2. No, that would be difficult. Strictly bigger than a half. Our estimates are not that strong. And then it'll follow that because we take medians, everything is good. Okay, so this should be pretty clear that this is fine, but let's go through the details. So the no collisions event was what? It's the event that for a fixed element I and a fixed row R, none of the head elements other than I hash into the same bucket. Well, the probability of collision for any given j is 1 over b. And b is at least 8k by our setting of parameters. So this happens with probability at least 7/8. Good. The second thing that we needed to hold was that the variance coming from the tail element is at most 1 over b fraction or so of the total tail. Well, that's just by linearity of expectation and Markov bound. In expectation, the variance is 1 over b of the total tail, and by a Markov bound, it's at least 1 over roughly that much. Good. So to summarize, conditioned on these events that hold with high constant probability, the following happens. The first term in the variance coming from the head is just 0. There are no collisions with the head elements. And the second term is small, roughly 1 over b of the total L2 squared mass of the tail. Cool. And now all that remains is to apply the small deviation event, which was basically that the basic estimator works. Putting all this together and doing some basic algebra, we get that good things happen with probability at least 5 over 8, and 5 over 8 is at least a half, actually bigger than a half. Fantastic. So then what we showed is that for any given item in the universe, and for any given row with probability at least 5 over 8, the estimate that we get is good. Since we have order log n rows and we do independent repetitions and take medians, this happens with extremely high probability for all items and all positions in the stream. This concludes the analysis. All right, any questions about the analysis? Okay, good. So let me make some remarks, state some related results. Yes?
So to actually use this, you have to know the universe, because you have to query every item in the universe to see if it's a heavy hitter or not.
Yes. Great point. The point was that to use, what we designed was a point query primitive, which, given an item, returns a good estimate for its frequency count. And the question is, how do you use this? Do you just go over all possible source destination IP packets? All right, that would take time. So in the context of a streaming application, you only use it for the items that appear in the stream. Right. So if I'm actually just scanning the stream, and
You can do it every time an item comes along.
right, yeah. So basically, items are coming along, and then I can just do this every time, and I swap it out. Right. If I find an item that my query says is more frequent than something else that I'm storing, I just swap it out. Yes.
So that works as long as it's only incremental. But if
Yeah.
you have deletions, it doesn't work. But there is a solution to a generic problem of having such a filter and finding the good guys. It's something I published together with Kapralov and several people here, and it solves that problem. How can you deal with finding the good guys in a filter over a huge universe?
Yeah.
It's using collision costs. Yeah, whatever.
More on that later. More on that
Oh.
later. So,
Oh, sorry.
yeah, I will not cover your paper.
It's just I was answering.
Yeah, of
Bob's
course,
question.
yes. Basically, there's the other question. So just to repeat Nicholas' answer here, the first answer to Bob's question is indeed that just query the item that comes in, but it is also possible to set up the sketch a bit differently so that you can recover the top K elements from the sketch itself without going through the entire universe. And that there's a whole industry and many amazing results. Very cool one by and Jelani and Kasper and others. Yeah.
So what do you assume about the hash functions?
Good. The question was, what do I assume about the hash functions? For the purposes of this analysis, we only need the hash functions to be pairwise independent. Right. Look at what did we use? We only had pairs of signs. As long as it's pairwise independent, everything is fine. Yes. Both for H and for the signs. In the next lecture, we'll talk about applications to linear algebra. We'll need a bit more independence there, and also more on that. Other questions? Yes.
Can you actually detect that most of the mass in the head of the stream?
Okay, good. Question was, is it actually possible to detect that most of the mass is in the head of the stream? Right. Yes, by running count sketch.
But I mean, but what if it's like, what if the head is bigger than you think by some amount?
What if the head is bigger? Then you'll know it, right? Then count sketch actually tells you that, right?
What?
If you run count sketch, and basically count sketch will tell you estimates for the head that are correct sort of up to the tail, very much, right? So when the head is bigger than the tail, you know that it is.
No, but okay, I don't get it. Sorry.
So I think your question was, is it possible to detect whether the head of the signal is bigger than the tail? Right. To make it concrete, for example, if the L2 squared norm of the top K elements is comparable as omega of the L2 squared norm of the rest. Was that the question?
Yes.
Good. And so the answer is, I think this answers your question, right? That you just run count sketch, and count sketch gives you estimates for the top K elements. And then you just look at the L2 norm of these estimates. If it's bigger, it satisfies your condition, then you're good.
Yes, but I mean,
If it's very small, then you'll not know.
no,
exactly how
but
small.
like if the stream does not comply, it might actually end up. I don't see why the structure cannot end up in a state that would look like the stream was good.
Okay, so it could be that the head is actually small, right?
Yes, but that's not a. Okay.
Let's
yes.
take it. Okay, let's take it offline because I do want to end this with a puzzle. That's important. Okay, I only have 2 minutes. Good. All right. So remarks related questions and a puzzle. That's very important. So first, coming back to Mikkel's point about deletions, right, and actually coming back to the title of this lecture series and what is sketching. Okay. So, one very important point to make is that the stream, the algorithm will work even if the items don't just arrive, but also depart in the stream. So here's another stream, wonderful. And then, oh, element 3 comes in with a minus sign, and the frequency reduces. All right, excellent. So the point is that if that happens, the algorithm works just like it did before. It's just that we don't add the sign, we subtract the sign. So the algorithm is linear in the input. That's fantastic, and that is exactly the idea of sketching, or linear sketching. Good. Good. So this is the idea of sketching, and this is what I will talk about for the rest of today. It's the idea of designing algorithms that are linear in the input. Our algorithms take randomized linear measurements of the input. Here's our sketching matrix. We'll instantiate this matrix at the beginning of the next lecture to stare at it a little bit. The space complexity is the number of rows in this matrix, and this x is really the frequency vector of the stream in our heavy hitters application. So because the algorithm is linear, it's very easy to maintain such sketches in the dynamic streaming setting. If items depart as well as arrive, we don't care. We just change a plus to a minus. Excellent. Couple of more observations before the puzzle comes. In the count sketch analysis, we made sure to distinguish between the head and the tail of the signal. In particular, our bounds on the precision of the estimates are depend on the L2 norm of the tail. This means that, for example, if the heavy hitters become very, very large, that does not affect the precision of our estimator. It doesn't get worse. Good. So suppose that S is a count sketch matrix with order k log n rows. I claim that we actually proved the following, that for every x in Rn, so not necessarily a frequency vector, the entries don't have to be integers, they don't have to be positive. If x hat is the estimated vector, as per our estimator, right, that just takes medians coordinate-wise, then the L infinity distance between x and x hat is bounded by 1 over root k fraction of the L2 norm of the tail of x. Okay. So this is known, this is all with high probability. So this is known as the L infinity L2 sparse recovery guarantee. Count sketch provides sparse recovery guarantees. Important thing to note is that if x itself had at most k non-zeros, then the right-hand side is actually plain 0. In particular, we showed that vectors with at most k non-zeros can be recovered from order k log n linear measurements.
Say that again.
All right. So I would like to point out that our analysis in fact works for any vector x, didn't use negativity, integerness, or anything. And I would like to point out that the precision of our estimates depends on the tail. So if the tail is 0, then our recovery is exact. So if the original x had at most k non-zeros, tail is 0, so we recovered the statement that k-sparse vectors can be reconstructed from order k log n measurements. The number of measurements can actually be made order k, so this application is off by a log, but it's still interesting. Good. Yes. So now, again, this L infinity L2 bound is known as the L infinity L2 sparse recovery guarantee. The number of measurements, the k log n rows, is actually optimal. So if we're not thinking about exactly k-sparse vectors where the tail is 0, but vectors that are close to k-sparse where the tail gets to be non-zero, then that's asymptotically optimal. That's a very nice proof of this, for example, given by Kandoba, Piotr Indyk, Eric Price, and David Woodruff in 2010. This basically follows from information theoretic statements about the capacity of the Gaussian channel, or the Shannon-Hartley theorem. Essentially, imagine that the noise, you can make the noise independent Gaussian, you can make the tail be independent Gaussians, and then every linear measurement that you take is basically some signal, which is what you're trying to recover, plus Gaussian noise, and that's why you can bound the amount of information that any measurement gives you using statements about the capacity of the Gaussian channel. A related guarantee is the L2 sparse recovery guarantee, and that just says that for vector, yes.
Sorry, just for the first observation, is there a smooth interpolation between the case when the tail is 0 and when it's not, and like characterizing the upper and lower bounds in terms of the log? Like, is there anything that is like parameterized by that and can kind of optimal in the region between?
Good. So the question was basically, is there a smooth lower bound? Because as I said, if the tail is 0, then you don't need the log n. That's what Aaron is saying. And when the tail is non-zero, you do. I think you can. I don't know where if it's written, but I think you can extract it directly from the table.
And their upper bounds also.
Yeah, I think so.
Okay.
Upper bounds, I'm not sure. But I think you can extract them from things that I know. Right. Yeah. Yeah. Okay, good. So then a related bound is the L2 sparse recovery guarantee that basically says that from order k log n measurements, you can recover an approximation x hat to x, which is on the whose precision and Euclidean norm is on the order of the Euclidean norm of the tail. Imagine basically taking this infinity guarantee and checking what it implies for k elements.
Range, so there's no k in observation 2.
There's no k in there is a k. Good. Mikkel's point was, is there a k in observation 2? There is a k because the right-hand side has a tail, and tail implicitly depends on k. Tail is everything but the top k. Great point. Good. Yeah, and of course you can also make this 1 plus epsilon. So the L2 sparse recovery guarantee in terms of the tail can also equivalently be restated like this. We can recover a vector, an approximation x hat to x, which is just almost as good as the best k-sparse approximation. Right? Because the L2 norm of the tail is actually the L2 quality of the best possible k-sparse approximation. That's another way of thinking what the tail is. Yes.
You said all this is linear, right? So does the tail depend on the absolute values of the entries, or just the actual entries? Is it like the top k in absolute value, or the top?
Okay, good. Question was, what is the tail? Again, the tail is the result of taking x and zeroing out the k largest coefficients.
Not absolute value.
No, you just zero them. Then you get some signal. You can measure whichever norm you like. All right. Yes. May I take 5 more minutes? All right, good. I do want to.
Presenting all day, I'm not gonna.
All right. There's some benefits. Okay, so here comes the puzzle. All right, it's a nice puzzle it's a nice puzzle. Count sketch for matrices. Right, so far we designed this count sketch algorithm that takes a vector x, applies some linear measurements to it, compresses it, and from this compressed representation we can recover the top few coefficients up to some error. Excellent. Now, suppose that I want to do the same but for matrices. Here's the question. There are parties, and think of them as it's a distributed system. They sit in different rooms. Every one of the parties has a vector, x1, x2 through xr. These are length n-dimensional vectors. There's a coordinator who sits in a separate room, and every party looks at their vector, uses shared randomness to compress the vector down to order b log n bits. Looks like count sketch. All right, words. So that's the type of words. So count sketch should fit the bill, so words. Okay. Now, once the coordinator receives these compressed representations of the vectors, the coordinator wants to find the largest entries in this matrix A. What is the matrix A? It's the sum of outer products of the xi's. Okay, xi transpose. And I want the same guarantees, or even slightly weaker. What is stated here, slightly weaker. I want to output an approximation a hat to A that is pointwise this good. What is this good? The Frobenius norm of a matrix is the Euclidean norm of this matrix, if you think about it as a vector. So that's really the count sketch guarantee. Right? Except I didn't write a tail here, just for simplicity. I could also ask for the tail. Okay, great. So how can you do this? What could these parties send? So, here's a picture. Right. So there are parties. They send something about their vector to the coordinator, and I only want a small number of bits to be exchanged. So order b log n words. So assume that the vectors are integer valued with poly n. Don't worry about bit complexity. Words are fine. What can they send? No, these are numbers. So absolute value.
The natural thing would be to do what you have just done.
Excellent. Thank you, Mika. So
That's a generic answer. You give any teacher.
very good. Okay, so every party, as Mika suggests, thank you, Mika, simply does count sketch of xi transpose. It just looks at xi and count sketches it into B buckets. Fantastic. But this is slow. I don't like that this is slow. Every party has a vector x as input. Why should they form xi transpose? It's annoying. So good. So to flesh out Mika's proposal, right? Well, we just do count sketch. So now our hash function maps the universe n times n, the entries in the matrix, the matrix slots to B buckets, and the sign function is from n times n to -1, 1. Fantastic. And then we can, for every B, form the right thing. So that's the count sketch. But I don't know how to compute this fast, because this is a random hash function. It looks like I have to look at every I, j. Not nice. So I want to make this faster. I don't just care about the compression. I also want the parties to be fast. Good. So I want every party to send not count sketch, but sum sketch. And I want to design the sum sketch. I'll almost completely design it, right? Instead of having one hash function that maps the n by n matrix entries into B buckets and and the similar sign function, I'll have two hash functions and two sign functions. There will be a hash function h1 from the rows to B, and the hash function h2 from columns to B, and two sign functions that also take the individual coordinates, not the pair, and map them to the sign. This is basically a tensoring of two count sketches. Now, now I'll define a structured hash function h that maps entry ij to h1 of I plus h2 of j mod b. And the sign function just takes the product. Fantastic. Good. And now we can do count sketch with this. That's my hash function. That's my sign function. And here comes the exercise. I claim that the parties can actually be efficient. That is, the parties can just compute count sketch 1 of x and count sketch 2 of x. And then they can somehow efficiently combine the two row and column-wise count sketches into a count sketch of the entire matrix. And I'll stop here. So half an hour to solve this.
Thank you. Questions?
Do you have any ideas on what the histogram of hit counts look like in real life?
The question was whether I have any idea on what the histogram of frequency counts look like in real life. They're not worst case. There are some works on this. So, for example, very often Unsurprisingly, they look like power laws, they look like Zipf-fin distributions, and things like that. I'll mention at the beginning of the next lecture that for these specific distributions, for distributions that do occur in real life, count sketch is actually significantly more precise than what we proved. It's more precise log factor. This is a result of a very nice paper of Minton and Price from I think so 12 or 13. In fact, there's a very recent improvement on this by Mikkel and company, which I'll mention as well. So yeah, there is work on that. There's a lot to be done. Yeah, so I'll say more at the beginning of the next hour.
More questions? All right, let's thank Michael again. So we have a coffee break until 11, and we'll be back then. In case anyone's wondering, the schedule for today is actually the same as the workshop schedule today. There's no event at the end, so everything's at the same times they were yesterday. Just Michael. See you all in 11.